Hi folks, today we're going to look at logarithmic equations, and these are equations that have logs in them already. Whereas yesterday when we dealt with exponential equations, there were equations that had exponentials, or x in the exponent, and we used logs to solve them. Logarithmic equations already have logs in them. So I like to think of them in two kind of types. There's what I call short, which are ones where not all the terms are logs. And then there are ones that I would like to call long, where all the terms are logs. It doesn't really matter what we call them, but they have slightly different approaches. So for short logarithmic equations, we're going to create a single isolated log term, and then we're going to convert to exponential form, which you might think of as bay. In long ones, we'll create a single log on each side, and then we'll drop the logs and solve. You always need to check your answers in a logarithmic equation because you're not allowed to take the log of a negative number. So you always check your solutions, and really you're checking, do they cause illegal operations? And again, that illegal operation is log of a negative, not okay. Okay, so let's take a look at a few down here. We've got 2 plus log base 3 of x equals 5. Let's see. Are all the terms logs? No, clearly they're not. There's a regular 2 here. There's a regular 5. This is what I would call a short logarithmic equation. So let's see what we're supposed to do. We're supposed to create a single isolated log term. So that means get this log base 3 of x on its own. To do that, I'll subtract 2 from each side. So I'll get log base 3 of x equals 3. And now I'm going to convert to exponential form. So remember, when we see this log statement, it means the base is 3. What we might call the answer in exponential form is x, and the exponent is 3. So let's rewrite that in exponential form. The base is 3, the exponent is 3, and the answer would be x. These two statements over here are equivalent to each other. One's just written in exponential form, and one's written in logarithmic form. For us to solve this, all we have to do is work out what 3 to the power of 3 is, which is no big deal. Right? That would give us x is 27. We think. Now we're going to check. So I'm going to check by putting this back in. Check x equals 27. So on the left side, I would end up with 2 plus the log base 3 of 27. On the right side, I'd end up with 5. And if you work this through, well, the left side is 2. The log base 3 of 27 is asking 3 to the power of what makes 27? So that would be 3. And yes, it works out. We get 5 equals 5. Left side equals right side. Most importantly, we can now say for sure this is the answer. It checks out. What we're really checking for, though, in our check is whether this right here is a thing, is a legal operation. Can I take the log base 3 of 27? Absolutely, because you can take logs of positive numbers, and 27 is a positive number. So all that check, it's up to you whether you want to show it or not. I think it's probably a good idea to show it. But the main thing is that it happens so that you can confirm whether your answer is correct or not. Let's do the next one. So we've got log base x of 4 equals a third. This is a short log equation because not all the terms are logs. So we can convert to exponential form. So I got bay here. The base is x. The exponent is a third. And the answer is 4. Okay. Some of you can probably solve this just by inspection. For me, what I'm thinking is I want x on its own. So if I've got x to the third, what do I have to do to both sides to make that an x to the power of 1? I have to cube it. And if I do it to one side, whoops, then I have to do it to the other side too. So 4 to the 3. That would make x to the 3 over 3, or just x, and 4 to the 3 is 64. Again, let me check this out. When I check, really I want to see what happens if I put in that 64. I'll have log base 64 of 4. Now, that really does work out to be a third, but the main thing is that that's okay. You can take the log base 64 of 4, and that's because you are taking the log of a positive number, and also the base is positive here. Okay, so it doesn't cause us any illegal operations. Lastly, let's take a look at log base 3 of 5. Now, some of you are going to have a fancy calculator, and you can just type this in. So I can get the log base 3 of 5. Here's my log base 3 of 5. Gives me an answer of 1.46 roughly. Okay, so that's my answer. And there's nothing to check here because none of the things that you were taking the log of were the variable. Nothing to throw back in. Now, some of you are going to say, well, I don't have a calculator that does that. So that's fine. You can treat it as a short log equation. Not all terms are logs, so we can use bay to write this as 3 to the x equals 5. And then from there, we can take the log of both sides. So we'd have log of 3 to the x equals log of 5. Okay, and then we can work that through. That means we can bring the x down and get x log 3 equals log 5. And divide both sides by log 3. So we'd have x equals log 5 over log 3. And then head to the calculator. And it's going to give us about 1.46. Log of 5 over the log of 3. One last way you might approach this very last one is by remembering the change of base rule. Okay, so our answer was the same. So last approach, there was a property that said you could evaluate these weird logs by just going log of the big number over log of the little number. And that will give us 1.46 from change of base rule. And maybe I'll write that change of base rule off to the side here. So change of base rule is that log base b of a is log of a over log b. So that everybody, regardless of the fanciness of their calculator, can easily evaluate this. Honestly, if it were me and I didn't notice all these things, I'd probably do the middle approach, the one where we go to exponential form. But either way is going to get us to the correct answer. Okay, moving along, we've got another logarithmic equation. So it says log of x plus 3 equals the log of 7. In my mind, this would be this type that I would call a long, though it's not going to take us very long in this case, logarithmic equation. All the terms are logs. So if all the terms are logs, then we're going to create a single log on each side. That's already been done for us. Now we can just drop the logs, because the rationale is that if the log of x plus 3 equals the log of 7, then x plus 3 must equal 7. And that's easy to solve. We get x equals 4. Before we go ahead and confirm this, let me check what happens when I put this in. Left side and right side. So I'd get log of 4 plus 3 and log of 7. Are those equal to each other? Absolutely. Okay, and I don't need a calculator to figure out that log 7 equals log 7. Everything worked out. I can confirm my answer of x equals 4 is good. And the main thing here that we're looking at is log of 4 plus 3, or log 7, on the left-hand side, is that a real thing? Is that a thing we're allowed to do? Yes, we can take the log of a positive number. So, even though that was called long, I don't think it was particularly long. Let's try another one. Logarithmic equations, long and short. Here we have log of x plus log of x plus 3 equals log 4. So are all the terms logs? Absolutely. This is another long one. Create a single log on each side. So on this left-hand side, we have two different terms. We have to put them together. And we do know some log laws. We know this one, log A plus log B. If you have the sum of logs, it's the same as the log of the products, or of A times B. So if I put these together on one side using log laws, I'll have log of x by x plus 3. The other side is just log 4. Now maybe I'll make that look a little nicer. That will be the log of x squared plus 3x equals the log of 4. Create a single log on each side. That's what I did. Now that we've got a single log, now we can drop the logs. Okay, so let's take away the logs. It's not that we're dividing by log. We're reasoning out that if the log of one side equals the log of the other, then the things inside the log must be equal. X squared plus 3x equals 4. Okay, and now we have a quadratic. Ooh, and maybe it's been a while since we've seen some quadratics. So remember, the technique for a quadratic is make one side 0. X squared plus 3x minus 4 equals 0. And then factor it. You're looking for numbers that add to 3, which is the middle, and multiply to negative 4, which would be the end. This is a short trinomial. Okay, the numbers that do that are going to be 4 and negative 1. So I can factor right away. Now remember that we're not done yet. We actually have to solve the elementary equations. So that means we've got x plus 4 equals 0, or x equals negative 4. A lot of people jump right to saying that. And x minus 1 equals 0. Minus 1 equals 0, or x is equal to 1. That's a lot of work. Okay? And since it's a lot of work, we're tempted to say, okay, we're done. Those are our answers. But we need to check each of them. And unfortunately, they're kind of hidden down here under my palette. So let me try this. Maybe up top, I'll check x equals negative 4. Okay. And then beside it, I'll check, in red, I'll check x equals 1. Those are our two possible solutions. And I need to put them in the original form of the equation. So on the left side, if I put in negative 4, I'm going to have the log of negative 4, because that's what x was, plus the log of, let me get rid of this, negative 4 plus 3, which would just be negative 1. And on the right side, I'd have log of 4. Now here's the problem. The log of negative 4 does not exist. That's undefined. Or if you put it into your calculator, let's try it. Log of negative 4. Negative 4. Not a number is what mine says. Okay? It's not a real number. So since we had to do some illegal stuff when we put in negative 4, what that tells us is that negative 4 is not an answer. So I'm going to cross it out. I'm going to make it really clear for my teacher that that's not part of the final solution set. Now I'm going to check x equals 1 in the same manner. So I'll have left side would be the log of 1 plus the log of 1 plus 3, that's 4. And on the right side, I'd have the log of 4. Right away, I see there's nothing illegal here. You're allowed to take the log of 1 because it's a positive number. You're allowed to take the log of 4 because it's a positive number. This is all fine. If you really want to, you can put these together with the product law and show that they are log 4. So left side equals right side. But if I were doing this check, right at this stage here, where we're showing that all of these things actually work, then I would say, okay, this x equals 1 does work. And so I'll head down here to where I had my answers, and I'll circle this, make it really clear. In fact, maybe I want to show that in the end, the only real answer is x equals 1, and I want it to be really clear that that's the case. So in this one, we ended up with a quadratic. We ended up with some solutions that didn't work, and we call these extraneous roots. Extraneous root. It's a fancy way of saying it's something that looked like it was going to work, but in the end did not. Okay, moving along, we've got another one here that has exclusively log terms. So this is probably going to be what we'll call a long log equation. And the technique is going to be make a single log on each side, then drop the logs. The problem in this one is this pesky 2. So that's no fun. What can we do about it? Well, we could make that 2 live somewhere else. From the power law, which says that log of a to the n equals n log a, we know that we could make this 2 live up here as an exponent. So I can rewrite this as log of x plus 2 all squared equals log of 16. Now it reads as log something equals log something else. This is fair. This is where we can actually drop the logs and then solve. So we have created a single log on each side. We have to deal with those coefficients. So what does that give us? X plus 2 all squared equals 16 when I drop the logs. Just be careful here. If you're figuring out x plus 2 all squared, it means x plus 2 by x plus 2, or x squared plus 4x plus 4. Okay? So that's what this left-hand side must be, 4x plus 4. And that's equal to 16. Oh, it's another quadratic. How exciting. So the technique for quadratics is make one side 0. So I'll subtract 16 from both sides. I'll get negative 12. From here, I'm looking for numbers that add to the middle. This is a short trinomial. And multiply to the last number, which is negative 12. And the two numbers that do that are negative 2 and positive 6. So x plus 6, x minus 2, meaning that our possible answers are negative 6 and positive 2. Those are the numbers that zero out those brackets. We still have to check. So let's check x equals negative 6. That would give us, from the original form, 2 log of negative 6 plus 2. Oh my gosh. We know that's no good. You can't have the log of negative 4. Now somebody's going to say, well, if you put it in the second step, though, it's okay. That's not how we check our equations. We check them from the original statement. So since this is bad, or what my calculator would call not a number, x equals negative 6 is not part of the solution. It's not okay. And you may be tempted at this point to make some sort of rule where you say, oh, it's all just, if it's negative, it's no good. We have to check whether it causes a negative in the original statement. So let's check the other one. And even though one of them worked, it doesn't guarantee that the other one will. Let's check this out. So check x equals 2. So on the left-hand side, I'd have 2 log of 4. And on the right-hand side, I'd have log 16. The main thing I want to notice here is that log of 4 is a number. Is a number. It's fine. Now we can go through more of the check and pull that 2 up front and see we'll get log 16 equals log 16 because the 2 can go up as an exponent. But the main thing is that it didn't cause us to break the law. And when it doesn't, that typically means that the solution is fine. So a few interesting things happened. Number 1, it didn't look like a quadratic, but it turned into a quadratic. Number 2, it had an extraneous solution. And I guess as a third thing, we could say that there are alternate ways that you could approach this. You could have multiplied both sides by a half to start with, and then dealt with the exponent on your right-hand side. I think I'll just leave it at this for now, but if you have an alternate approach, feel free to use it. All right, here's another one. We have log of x plus 4 equals 1 plus log of x plus 1. Okay, let's see. What type is this? Is it a short? Short means that not all terms are logs. Yeah, that's true here. There is a regular 1. So we're going to call this a, quote, short log equation. So now we have to create a single isolated log term. And what that's going to mean for us is that we have to subtract log of x plus 1 from both sides. I want to get all my logs on one side and all my numbers on the other side. So let's see what that looks like. Log of 8x plus 4 minus log of x plus 1 equals 1. Okay, we still haven't created a single isolated log term, but we have got the logs all on one side. You might recall, though, the quotient rule of log laws. So we end up with log A minus log B is log A over B. That's something that you can exploit here. You can combine those two logs into a single quotient or fraction. Okay, so we put them together. Now we have a single isolated log term. And then the other side is just our numbers. The most common mistake I'll see here is people just drop the log. But there's no log to drop on the right side. What you need to do is convert to exponential form. Okay? And when we do that, we really mean bay. So let's, oh dear, there's no base shown on this. If there's no base shown on a log, the base is assumed to be 10. So this is a base, an answer, and an exponent. Let me put it in those terms. So I'll have base is 10 to the power of 1 equals the answer of 8x plus 4 all over x plus 1. Okay. Or I guess if I get rid of that exponent, it's just 10 equals 8x plus 4 over x plus 1. Now, at this point, it may look unpleasant because of that fraction, but it's not actually difficult to deal with. We hate the fraction in the equation, so let's just times both sides by x plus 1. And here's what will happen. Let me follow this through. We'll have 10x plus 10 equals 8x plus 4. For all that miserable stuff, in this case, we don't have a quadratic. I'm just going to put my x's on one side and my numbers on one side. So let's see, I'll get 2x equals negative 6, or x equals negative 3. Now remember, as soon as we find that answer, we're not done. We have to check it. So let me start to put it in the left side. Log of 8 by negative 3 plus 4. Does that equal 1 plus the log of negative 3 plus 1? Now, some of you might see it right away. This is telling us log of negative 24 plus 4 or log of negative 20. No, that's not a thing. Can't take the log of a negative number. So what does that mean? We ended up with x as negative 3 maybe as a solution. It didn't work. So our only possible solution didn't work. What do we say? No solution, or no roots. So we just go through the process of looking for an answer and then checking it and disqualifying anything that doesn't actually work in the original. We'll keep trucking here. Short or long, let's see. All we're asking is, are all the terms logs or are not all the terms logs? Let's see. Oh, not all the terms are logs because there's this 3. So we're going to create a single log on each side. Look, I have 2 logs that are being added, so I can combine those together using log laws. It's going to be log base 2, the base will stay the same, of one thing times the other thing. That is straight up just using the log property of log A plus log B equals log AB, or the product rule. All right, so we've got a single isolated log term. You can FOIL it out if you want, or we can do that later. Now we have to convert to exponential form. So here's my base. This whole mess is my answer, and there's the exponent. Let's put it in exponential form. So 2 to the 3 equals x plus 4 by x plus 2. Let's just work this out. That 2 to the 3 is 8. This will be x squared plus 6x plus 8 when I FOIL it out. And now again, it's a quadratic, so I make one side 0. Let's see what happens. So I'll get 0 equals x squared plus 6 when I subtract 8 from both sides. Sometimes people get confused about factoring here. Remember that the first type of factoring you always look for is greatest common factor. So I can factor this as x by x plus 6, which will give us answers of x equals 0 or x equals negative 6. Or sorry, potential answers. Okay. Now, you're not allowed to take the log of 0, but that's not what the issue is. The question is, if you put in 0 for x, will it cause problems for you? So let's check x equals 0. It would be the log base 2 of 0 plus 4 is 4, plus the log base 2 of 0 plus 2 is 2. And we're wondering, is that equal to 3? These are both okay. You can take the log base 2 of 4, because 4 is a positive number. You can take the log base 2 of 2, because 2 is a positive number. So 0 actually works for us. That's an answer. Let's do the same thing, checking for x equals negative 6. And right away, I'm going to have log base 2 of negative 6 plus 4. Well, that's negative 2. No, not okay. So that means that negative 6 is not an answer. And I'm not going to let my teacher wonder whether I still think it's an answer. I'm going to X it out real hardcore. Boom, not an answer. And then I'll either circle or box the thing that is my answer. One last one. So logarithmic equations. Short or long? Let's see. Are all the terms logs? Yes, they are. So this is what we might call a long. Create a single log on each side. Oh my, look, we've got 2 logs on the left side, but I can put them together using quotient law. Now, alternately, I could put the log base 4 of x on the right-hand side and put them together with product rule or product law. But I think this is pretty straightforward. So I'm just using the property that log A minus log B is log of A over B. That's one of our log laws. I created a single log on each side. Yay! Now I can drop the logs. So I'll get x plus 3 over x equals 2x. Okay, that's kind of weird, but fine. Let's go with it. And we have to solve. So when I look at this, I think, oh, I really hate that x on the bottom. I don't like that fraction. So I'm going to times both sides by x. And so what I'll end up with is x plus 3 equals 2x squared. Oh my, it's a quadratic. So I'll make one side 0. 2x squared minus x minus 3. Now we'll try and factor this thing. I don't know what your favorite technique for factoring a long trinomial is, whether it's by guess and test or whether it's by decomposition. It really doesn't matter, whichever one you prefer. I can throw a link to some factorization videos down below, but we've done a bunch of this with trig stuff. So it does factor to 2x minus 3 by x plus 1, and that means that the potential solutions come from 2x minus 3 equals 0, which means that 2x equals 3, or x is 3 over 2. And they also come from x plus 1 equals 0, or x equals negative 1. Those are sort of our candidates. Okay, let's see what happens. I'm going to check x equals 3 over 2. And I'm just looking for illegal stuff. So I'd have log base 4 of 3 over 2 plus 4. Is that okay? Yeah, that's definitely a positive number. Let's keep going. Minus the log base 4 of 3 over 2. Again, that is a real number. You can take the log of a positive. And then I'm wondering, is that equal to, if I sub in that 3 over 2, it would be log base 4 of 2 times 3 over 2, or just 3. That's also okay. Putting in 3 over 2 did not cause us to break the law at any point. Therefore, 3 over 2 is a solution. If you want to go further and fully verify that, that's fine. You're welcome to. But really, we're just looking out for illegal operations. All right, let's similarly try x equals negative 1. So maybe I'll do that in a different color. Check x equals negative 1. So that would give me the log base 4 of negative 1 plus 3. That's 2. That's fine. So everything's all right so far. Let me put in the next one. Then I'd have log base 4 of negative 1. Oh dear, that is not a thing. No. Can't take the log of a negative number. Therefore, this is not part of the solution set, the negative 1. And the only answer is positive 3 over 2. Again, there are alternate approaches you could take for doing this, but I think it's fairly straightforward to just use the quotient law. So that brings us to the end of the lesson on these logarithmic equations. Again, notice that there are two types. You're asking yourself whether all the terms are logs. If they are, then you've got a long one like we just did here. If they're not all logs, then make a single log on one side and use bay. Remember to always check your solutions to make sure you're not being asked to take the log of a negative, which is not okay. As for practice, we're looking at the textbook, page 412 to 413, numbers 1, 4, 5, and 8. And let's say that 8E is for fun. I hope you found this helpful, and good luck with the material.